Good morning, everyone. Today we are going to continue the examples that we had about calculation of deformations in structures. And as you remember, we were talking about energy methods, and we talked about the virtual work method. And the other method that we had was Castigliano's second theorem. And these are the examples that we are going to solve to review these methods and see how we can use them for finding deflections in different structures. In the first three examples, we used the virtual work method, and over here you can see we have a beam. And as you remember in the presentation files that we used for discussing the methods, I looked at this beam and solved this problem by using Castigliano's second theorem. Now I'm going to solve the same example, but the method that I'm going to use is the virtual work method. So you can compare the two methods and see how different they are and how much effort we need in using the methods for solving problems. So over here you can see the beam is given to us. It's a beam with two supports. We have a hinge support at the left and a roller support over here at point B. The loading is given and the question is asking about the deflection at point C, which is this point over here. So, as you know, whenever we want to use the virtual work method, there are two major steps that we have to have in our solution. The first step is to analyze the structure under the given loading. In this specific situation in which we are dealing with a beam, I have to find the bending moment equation for the beam under the given loading. That's the first analysis attempt. The second one is removing the loading and applying the virtual method. Applying the virtual load. Once you do that, you can analyze the structure under the virtual loading or the unit load in that specific location where we want to know the deflection, and then we have to use the formulation for virtual work method for finding the deflection. Over here you can see we have the structure under the actual loading, and all I need to do is to analyze this beam and find the terms for moment, bending moment in this beam. That's what I have over here. You know how to analyze a beam under any load and find the equation for bending moment. The second step is to remove the loading and apply the virtual load, which is this unit load at point C, which we want to know the deflection. We want to know the deflection at point C, right? So I applied the unit load at point C, as you can see over here. Now I have to analyze the beam under this loading and find the terms for moment. And this is MV, the virtual moment, because we are analyzing the beam under the virtual loading. Once I obtain these equations, I can simply use the table that I used to use in my previous examples. And you can see I have the different segments. I have the different origins because I just decided to have the equation for bending moment in this segment from point C and in this segment from point A. And over here you can see the equations that I found for each of the bending moments under different loadings. Now I have to use the equation that we have for virtual work method. 1 multiplied by the deflection is equal to the integral of moment because of the virtual load multiplied by the moment because of actual loading divided by EI multiplied by dx. Once I do that, I can leave the EI term outside the integration because it's a constant value, and I'm performing the integration over the domain that I have in the beam. I consider two domains, one in this portion, one in this portion, or BC. and these are the integrations. You can use your calculator or you can use your knowledge in calculus to perform these integrations, but once you do that, you can see we have this term on the integration side of the equation. I have to just include the value of EI, and once I do that, I can find the deflection at point C as minus 0.194 inches. This is negative, which means that the direction of the deflection is in opposite to the direction of the unit load that we applied as the virtual load. I applied this unit load downward. I got a negative deflection, which means the deflection is upward. This is how we can use the virtual work method for finding the deflection in beams. Let's move to the next example, which is this frame, and now I'm going to use Castigliano's second theorem for finding the deflection in this frame. As you know, whenever we want to use Castigliano's second theorem, we are using a method based on the principle of energy conservation in structures. And as you know, the Castigliano's theorem or Castigliano's second theorem was about the derivative of the strain energy with respect to a force. As you remember, we talked about partial derivatives in the presentation file, and we said if we calculate the partial derivative of the strain energy with respect to a force, it will give us the deformation in the same direction at that specific force. That was Castigliano's second theorem. And the first theorem is some rule about the equations of equilibrium, which is not going to be discussed in this topic. But now that we know about the theorem and Castigliano's second theorem, we can use this in this method, in this problem. As you can see, this frame is given to us. We have the loading, we have properties of the material, and the question is asking about the vertical deflection at joint C. How should I use Castigliano's theorem for solving this problem? The first step is to analyze the structure. This step is similar to the virtual work method. The thing is that in the virtual work method, we had to analyze the structure twice. First, it was analyzing the structure under the given loading. Second, it was analyzing the structure under the virtual unit load. When we are using Castigliano's second theorem, I have to analyze the structure just once. And the thing that is important in this method is to include the force, or in cases where you want to find the rotation, the moment in that specific point in which you want to know the deformation, which can be deflection or rotation. But I have to apply that force. For example, in this example, I have to include a P force at point C, and then based on that P force and the influence of it on the moment diagrams of the members in the frame, I have to use the equations of Castigliano's second theorem. So over here you can see I have the structure under the loading. I did include the force in the place where the deflection is required. Later, when we want to calculate everything as the very final step, we can set the value of P as 0. But at this moment, we have to put the force in the place where we want to know the deflection and find the bending moment equation and everything else in the members based on P, as a function of P. That's what I have over here. As you can see, I did find the reactions in the support based on P. And I also found the bending moment equations in all the members as a function of P. Over here you can see I did not include the axial force because, as you can see in the information about the material properties, we don't have any information about the cross-section area, which implicitly means that we don't need to include the equations for axial deformation in the main equation for Castigliano's second theorem, this equation. If you look at the presentation file, I showed you two sort of equations. The one was when we have only the calculations based on bending moment, and the other one was the situation of including axial deformations in the analysis. Over here, we are just looking at the bending moment properties, and that's why I only calculated the bending moment in all the members. So based on the loading, we did analyze the structure. We could find the equations for bending moment based on the loading, and also this P force, which is the key piece of information or the key movement in Castigliano's second theorem. That's the key thing that we need to have whenever we want to use Castigliano's second theorem and use the equations for this method. So these are the analysis results, and now I have to put them in the table which summarizes all the information that I need for using the methods. We have the information about the different segments in the frame, the equation for bending moment, and this important piece of information, which is the partial derivative of bending moment with respect to that force. Now that I have everything, I can use Castigliano's second theorem and the equation that we had for that. This is the equation. I can just put the terms that I found in my table over here, and then at the very end, when I'm performing the integration, I can include the value of P and then find the final value as the result of calculations as this value. The remaining step is just including the value of EI. After including that, you can see I found delta as 2.39 or about 2.4 inches. This is positive, which means that the direction of the deflection is in the same direction as the P force that I applied at the beginning of the analysis. In this specific example, the actual loading did not have any point load at point C. That's why I applied the P, and at the end in the calculations, I set the value of P as 0. If we had some loading as a constrained load, concentrated load at point C, I would set the value of P as that specific force at point C. For example, if I had a 10 kip force at point C, I would set the value of P as 10 kips. But in this specific example, we didn't have any force at this point or point C, so the value of P is set to be 0, and that's what we have over here in this equation. This is how we can use Castigliano's second theorem for finding the deflection in a frame. As you can see, the method itself is not difficult. You can simply incorporate it in your calculations and finding deflections. The only thing that might take some time is just the analysis itself. And I believe at this time you are familiar with the analysis procedure, since we talked about it in the fourth chapter when we were talking about beam and frame analysis. But this is the application of Castigliano's second theorem for finding the deflection. For just having some training, you can look at this example and use the work energy method for solving this problem. That can be a good training and also can give you more information about the methods that we have for finding deflections, and you can compare them and see how the procedures are different, and also you can compare the accuracy of the methods in terms of the changes that you can see in the final value for the deflection. So this was the fifth method, the fifth example, and let's move forward to the last example, which is this example here. we have a truss and I want to use Castigliano's second theorem for finding the horizontal and vertical components of the deflections at point B. We did solve several examples about using work energy method or virtual work method for finding the deflections in trusses. And over here you can see the other example. The only thing is that we want to use Castigliano's second theorem for solving the problem. It is very important for you to understand the difference between these methods, and there will be definitely one truss in your final exam and you have to use one of these methods for solving the truss. I will specify the method that you have to use for analyzing the truss and solving the problem and finding the deflections, but you need to become completely familiar with these methods and you have to fluently use these for solving problems. So this is the truss. You can see the loading. We have one vertical load at joint D and another vertical load at joint B. We have a hinge support at this point over here or joint C and a roller support at joint A. The question is asking about the horizontal and vertical components of deflection at point B. As you remember, if we wanted to use the virtual work method, we had to have three analyses for this truss. The first was analyzing the truss under the given loading, which is this loading. The second was analyzing the truss under a unit horizontal load at joint B. And the third was analyzing the truss under a unit vertical load at joint B. That's the case if we wanted to use the virtual work method for solving this problem. Now we want to use Castigliano's second theorem, and I have to analyze the truss only once. But the thing is that I have to include two loads. One vertical force at joint B and the other one is a horizontal force at joint B, and both of them should be in terms of a parameter like, for example, P1 and P2 or PH and PV. As you can see, that's what I have over here. So I have analyzed the truss under the loading, and as you can see, this loading is this force that we already had at joint D and also two forces at joint B. One of them a horizontal, which is P1, and the other one a vertical, which is P2. Of course, based on the loading that we have on the truss, this P2 will be set equal to 45 later when we are calculating the final value of deflection in the Castigliano's theorem. But this is the situation as the loading on the truss, and now I have to analyze the truss on under this loading. As you can see, the analysis is done, the results are shown, and in this table over here I have listed all the members, the information about the members, the forces after the analysis, and these terms are based on the equation that we have in Castigliano's theorem. So as you can see in the equation, I have this term, which is round off the force with respect to P1. This is one equation, and the second equation is the round or the partial derivative of the force with respect to P2. This goes back to that discussion that we had in the very beginning of this chapter, which I said whenever we are using the work energy method, we have to have different attempts in terms of the calculations for finding different deformations in the structure. So this is the forces that I could find based on the analysis. This is the partial derivative of the force with respect to P1. This is the partial derivative of the force with respect to P2. And then these are the terms that we have over here in the equation. the values are calculated in these cells, and these are the summation of these values. Now I have to return these values into these equations, and then I included the value of EA and found the deflections. And over here you can see these are the deflections as the horizontal and vertical deflection at point B. The positive values means that the deflections are in the same direction as the loads that I applied in the beginning of the analysis. The procedure, I believe, is pretty straightforward. The thing is just performing these steps, following these steps, and doing the calculations and making sure that you understand the procedure and you know how to, for example, calculate the partial derivative and how to put them in the equation for finding the deflection. As you can see, these examples, just presenting them does not take much time. The important thing is to write them on the paper and repeat these examples at home. That's why I leave more time than previous sessions in this presentation for you. And I really want you to spend some time on repeating these examples at home, because these are new stuff, the stuff that we talked about in the last chapter, which was about deflections based on geometrical methods, and in this chapter, which was about energy methods. I want you to spend more time than usual for repeating these examples at home, and I'm available. You can right now send me an email and say, for example, I have a problem about this, or I have a problem about that example. We can definitely discuss that through email, and if necessary, we can set a time for WebEx meeting and discuss that through WebEx. So please take the rest of the time and solve these examples at home, and let me know if you have any problem about solving them and following the procedures. Thank you.